Hey guys, welcome to our project. This is Group T4C. Our topic is FPGA-based acceleration of Canny edge detection. So here's our design overview. Our ultimate goal is to develop an Canny edge detection project that is not only optimized for performance, but also implemented on the specified FPGA board. So here's kind of examples. Firstly, we got kind of grayscale images here. After our Canny edge detection algorithm to process these grayscale images, finally we got kind of edge detected images as shown here. So here is some background information of our algorithm. Firstly, we got data input as the source file to feed them into the Canny edge detection algorithm. So in the algorithm, the first step is to conduct the Gaussian smoothing, which is to blur the image, and then we use the Sobel operators to detect the edges. And after that, we come to the non-maximum suppression, which is to find the local maximum in the gradient magnitude. After that, we do some zero padding to kind of restore the image back to the original size. After that, we did the edge tracing by connectivity analysis to connect the strong edges and the weak edges. Eventually, we got the data output, which is the edge detected images.
Okay, so for implementation, we can draw a flowchart that can illustrate the whole process of our design. Well, first we will read 25.6 by 25.6 RGB image and convert it into some grayscale image using OpenCV, and then we will let the system read the input file and store the pixel values into arrays and go through this pixel values in the array and pack each 4 pixels as a group to be written into the input string. And then after we finish the pack stop, we then transmit these groups to the edge detection process modules and conduct the edge detections process. And then we finally we processing the data pixels, and we will get the output pixels value, and we also will write them into output file in the format of dat file, and we will read the output file and transmit into the image. Okay, and this is our baseline design. It's the kind of a high-level diagram that can illustrate the architectures. Well, first we will let the ARM processor send the data sent to the FIFOs with the size of 32 bits, and that is 4 pixels at one time, since we used an unsigned 8-bit integers to represent each pixels. And when it comes to the accelerators, we will first organize all the pixels into an array and transmit the whole arrays between each sum modules. And then after the processing, we will also need to split the array into the string, which can let them to meet the bandwidth of the FIFOs and transmit it back to the ARM processor.
So we got in total 3 major optimizing strategy, which is the first one is the parallelism, and the second one is the distribution memory access, and the third one is the data streaming with custom numerical types. And we're gonna discuss the detail below. So the second version that we have for this optimization, the HIS line and window buffer design. So as you can see here, we utilize the line buffer and window buffer to speed up the process, which means we're only gonna read one data input at once instead of reading the entire array again and again. So here is a simple demonstration that how the line and the window buffer gonna works. As you can see here, it's a simple line buffer. What we're gonna do is we're gonna move this one up by 1 row, and then put the new data into the bottom row. And then we finish new line buffer. For the window buffer, what we're gonna do is move the window buffer to the left by 1 column. And then what we're gonna do is we're gonna move the created line buffer into the empty space of the window buffer. And then we got an entire new window buffer, which means we have to read in one data and complete one cycles.
Okay, and beyond the line buffer and the window buffer, we also introduced the data string to further optimize our design. Well, that is, we instead of using the whole bunch of array to transmit between each submodules, we only transmit 1 pixels at one time to significantly reduce the resource usage of our design. And for each pixels, we kind of pack them into a specific format that is containing 4 fields. The first field of pixels is also an 8-bit integers. And for the second and the third field is the corresponding row and column of these pixels. And we will use them for updating and leveraging the line buffer and the window buffer for each module. And then for the last fields, we also introduce gradients, which will only be used in the Sobel and the NMS modules.
So by changing the data flow, implementing the, line buffers, window buffers, and using HL's accelerations, we achieved about 7 times acceleration compared to the baseline design. And we also reduced the VRAM usage from 83% to 5%. And in order to let everyone see the difference between various design more clearly, we made the collected data into 2 charts. The left one is about the latency, and the other one is about the area usage. In this final lab, we have optimized the 3 versions of implementations. The first version is directly based on the open source code. And in the second implementation, we added line buffers and window buffers to handle the memory. And in the third implementation, we changed the data flow to reduce the II of each functions. And in this way, we can further improve the throughput of the implementation. So, and for the future design, we can also do some like a real-time image capture, and we can finish it by connecting the camera and design a Python script to do that. Okay, so that's all of our presentation. Thanks for watching.
Okay, now so I will demonstrate how our design works. First, we got 4 different original pictures with a size of 25.6 by 25.6, which has been converted into 4 grayscale image. And we have converted the pixels of each grayscale image to this dat files with a series of pixels here. And now I will demonstrate that how these files transmitted into the FPGA board, and the FPGA board can output some correct results. And now I have get a result images that file as illustrated here, and I will transmit these files back to our processor. And now the result has been transmitted into this file result directories, and I will use this Python script to illustrate. Okay, now here is the edge detections pictures as illustrated here compared to the original pictures here. We have transmitted 4 pictures.